Hi everyone, my name is Ki-gon. In this session, we would like to introduce a new exciting open source toolkit with some really strong performance capabilities. It's called cuCIM, and that's what this session is about. I'm presenting here with my colleague from cuCIM, Gregory Lee, who is collaborating with me and other teammates of mine at NVIDIA on this toolkit. Throughout the presentation today, you are going to learn about what is cuCIM, compatible APIs for OpenSlide or scikit-image, NVIDIA accelerated operations for both I/O and image processing, a couple of demos, and then we will teach you how to get started with it. In large image processing, there are a few challenges. In a typical deep learning pipeline, a lot of time we spend on I/O. For example, a use case that shows such issues very well is loading and decoding huge image files in digital pathology. And these image pipelines often take advantage of image processing techniques that are only available on the CPU. In summary, the existing techniques are missing a capability that combines advanced I/O handling with scalable GPU processing. These two problems became a lot larger when we deal with large 2D, volumetric, or general n-dimensional data sets, which are highly common in bioimaging, medical imaging, seismology, astronomy, geospatial, and many other use cases. To address the aforementioned problems, cuCIM is introduced. First, OpenSlide is a well-known library to read whole slide images, which usually are image pyramid and tiled TIFF-like images. cuCIM provides an OpenSlide-like API for loading various image formats, including whole slide images, fast. Second, including other image processing libraries such as OpenCV and ITK, scikit-image is a popular Python-based image processing library and provides a collection of useful algorithms for image processing. cuCIM provides a scikit-image compatible API with GPU-accelerated image processing. cuCIM is designed to provide GPU-accelerated I/O, computer vision, and image processing primitives for n-dimensional images, supporting easy-to-use APIs that can also replace aforementioned CPU-based libraries. This is the high-level cuCIM architecture. On top of cuCIM is built on top of great libraries such as cuFile, Nickel, and Carbonite SDK from NVIDIA. cuCIM primarily falls into three layers. Core layers offer both C++ and Python API for features such as image file I/O and image operations, as well as file system through cuFile. On top of those two layers, it provides a Python API covering a growing subset of scikit-image using cuFile. Combining with Dask, a flexible parallel computing library, greater acceleration is possible through distributed and multi-GPU computing. Here is an example of how we are providing OpenSlide-like APIs. Code on the left side loads a partial image from a TIFF file using OpenSlide, and the code on the right side does the same job, but with cuCIM. As you can see, cuCIM is able to load an image using OpenSlide-like API. And if your application is written with OpenSlide library, You can easily port your app with minor modifications, such as changing package name or the way to access metadata. cuCIM also supports a cache mechanism to avoid redundant loading of the same tiles in the image. You can choose one of those three strategies for cache. If a cache is used, you can accelerate loading images when you load multiple partial images during training or inference workflow. So here you can see the hit count of the cache would be increased when you try to load the same region of the image twice. cuCIM also supports array interface and CUDA array interface for interoperability with other AI frameworks. This example shows how an image loaded by cuCIM can be converted into CuPy's anti-dimension array object, processed with cuCIM's image processing algorithm and visualized. Here, we read a specific region of the image. Since the object returned by read region supports array interface, it can be transferred to GPU memory by using cupy.asArray method. And then we are calling resize function, which is one of the transform functions in cuCIM. If you want to plot that, we need to use get or cupy.asNumPy method to transfer this back to the host for visualization. GPUDirect storage, abbreviated as GDS, is NVIDIA's capability of loading the images from an existing storage device directly into GPU memory, and doing that very efficiently. Here is how we have integrated cuCIM with the cuPy API and the GDS for accelerating your I/O. cuPy driver class provides two primitive APIs, which are pread and prewrite, that you may find similar ones in POSIX APIs. Using the APIs, here you can see that you can read file contents directly into cuPy's array or PyTorch's tensor, which is in GPU memory. Also, you can write buffers in GPU memory into the file system directly.
So as Gigon mentioned, cuCIM implements a substantial subset of the scikit-image API, enabling rapid porting of existing scikit-image-based codes to the GPU. The cuCIM skimage module is built using cuPy and typically gives much better performance than the corresponding CPU-based implementations that are in scikit-image. Other Rapids libraries provide complementary functionality that can be combined with cuCIM in applications, for example, cuML for machine learning or cuGraph for graph algorithms. Next slide. So I want to show now a very simple example involving contrast adjustment in both scikit-image, shown on the left, and cuCIM on the right. And in this example, we load a grayscale image of the moon that's distributed with scikit-image, and then apply 3 different methods of contrast adjustment. You can see that this code is nearly identical with only the following changes. First, the top-level imports change from NumPy to cuPy, and we import the exposure module from cuCIM.skimage. Here, the dataset itself is loaded from an image file on the host file system, so we have an additional call to cupy.asArray to transfer to the GPU, and then we form 3 different rescaled images, where the rescale intensity function does a rescaling based on a percentile of the original image intensity values. The second is a histogram equalization method, and the third is a locally adaptive version of that. So on this slide, we can see the output of this, which exactly matches the corresponding example from the scikit-image on the CPU, where we have a low contrast image that's been stretched. Its contrast range has been stretched in 3 different manners, as shown here. So this slide is just highlighting that we have a large range of functions implemented across many of the different subpackages of scikit-image, from basic things like filtering and morphology to kind of more involved high-level things like restoration, registration, or segmentation. So as we saw in the previous example, cuCIM's scimage API operates on CuPy arrays. And a nice feature of these arrays are that they support both DLPack as well as the CUDA array interface protocol for good interoperability with many other GPU-accelerated Python packages. These include not only the Rapids packages mentioned previously, but also Numba, as well as popular deep learning frameworks. Another feature we'll demonstrate more later in the talk is the ability to perform distributed computations on large data by use of cuCIM in combination with Dask. So we're now going to start to take a look at performance in the areas of both I/O and image processing. So on the image input side, we take a look at an application in digital pathology. Here, the pathology slide data are stored on an SSD drive, and we read all patches of shape 256 by 256 from a large TIFF image. The performance here is compared to the OpenSlide library as well as raster I/O, and all performance values are relative performance as compared to OpenSlide. cuCIM shows consistent improvement in performance over OpenSlide and raster I/O in both the single process as well as multi-process cases. So on this slide, we look at the relative benefit of GPUDirect storage that Gigon presented earlier in reading a large 2 GB binary file directly from an SSD drive to the GPU. So we bypass the host here. And in this example, GDS provides a 27% acceleration over use of standard CUDA memory copy calls. On this slide, we are highlighting the performance of several of the low-level image processing operations in cuCIM's scimage module. All the values shown, again, are in terms of a relative acceleration as compared to scikit-image on the CPU. So for example, a value 100x on the plot means the operation is 100 times faster on the GPU. And note that this y-axis on these plots are on a log scale. So we show results for both an older generation GTX 1080 Ti GPU as well as a modern A100 data center GPU. The functions profiled here include color conversions, filters, and labeling of connected components. And in these benchmarks, the A100 substantially outperforms the 1080 Ti, but both GPUs provide a large acceleration over scikit-image, ranging anywhere from factor 14 for labeling the connected components to greater than 1,000-fold acceleration of median filtering with a small footprint on the A100. So it's important to note here that these times don't account for the transfer of data to and from the GPU. We did this because we're considering a common scenario where the data transfers will be minimized by remaining on the GPU for several subsequent operations in an image processing workflow, with transfer back to the host occurring only at the end. So on this slide, we look at just a few additional results of some higher level operations, such as total variation denoising, Richardson-Lucy deconvolution, active contours, and rigid image registration. And these operations all show good acceleration over their CPU counterparts on both GPUs tested. Next slide. Yeah. So for this last performance slide, I want to highlight some work that was contributed back upstream to the CuPy library itself. And specifically, we created an n-dimensional implementation of spline interpolation following SciPy's API. And these functions underlie operations like rescaling and image pyramids in cuCIM. The cases plotted correspond to affine transforms of order 0, 1, 3, or 5, as well as a more general deformation via map coordinates. And all of these operations see substantial acceleration on the GPU, often exceeding 100 times. So we're going to now move on to some demos of the cuCIM API. And this first demo is related to the image I/O with the OpenSlide-like API. Okay, we're going to look now at browsing of multi-resolution TIFF images in Napari. In this case, it's a digital pathology slide, which is a couple 100,000 voxels in the vertical dimension here. So if we were to open this in Napari itself without any plugins, it's going to end up taking a lot of memory. In this case, about 50 gigabytes, and it has a delay of about 45 seconds on opening it. And so one way we can improve on that is using a plugin. We use here Lazy OpenSlide, which was created by Trevor Mans. And this uses the OpenSlide library to load just the regions of the TIFF file we need on demand. So when we're zoomed out like this, we're loading a lower resolution representation. And then if I zoom in on a particular region here, it's going to progressively load higher resolution data just for the region that I'm viewing on the screen here. And so that allows us to look at any particular region at high res without loading the entire thing into memory at once. And so this is pretty nice. It allows you to browse around. The one drawback is that you can see that scrolling is not so smooth here, and we're getting a frame rate of around 1 frame per second as reported by this measure FPS function from the underlying VisPy library. And so if we were to look what this plugin is actually doing, it's using Napari's standard reader plugin framework where it tries to open a given path with OpenSlide, and if it's able to do that, it's going to pass on to this custom reader function. And that reader function, I don't want to go too much into the details of how this works, but it's basically going to represent this multi-resolution TIFF file as if it was a ZAR store. And ZAR is something that's understood, can be mapped to a Dask array, and these Dask arrays can be used to build this multi-resolution pyramid that Napari knows how to work with. So we want to look inside this ZAR store class, and the key functionality in there is this OpenSlide method called readRegion, where we're just going to, when the viewer selects a particular region, we're going to load at some offset into the file. So we have some location offset. We're going to read a tile of a particular size and at a particular resolution level. So we have that same kind of function in cuCIM. So you might think we can adapt this plugin pretty easily to use cuCIM on the back end rather than OpenSlide. So if we look at how to do that, we change here. We need to import cuCIM. We fall back to OpenSlide if it's not available. There's a few other places where we access attributes of the slide, and the API is slightly different between these two, so we have to adapt this correspondingly to retrieve things like the level count or the dimensions. But the only other change that's really needed is when we open this path, rather than using OpenSlide, we use cuCIM's cuImage class, and then that class has this same readRegion method. And so we don't have to change the rest of this plugin, it should just work. And so if I open another copy of Napari here that is using that version of the plugin, everything is conceptually the same, but when I browse and move around here now, it's quite a bit smoother than before. Not quite as smooth as you might desire, but it's getting now around 5 frames per second rather than the kind of 1 frame per second that we were seeing previously. So this is pretty nice, and should point out at this point that everything's still on the CPU. There's no GPU capability being used. It's just the TIFF reader built into cuCIM is fairly efficient for this application. Okay, so now we have a second example of how we can do some interactive image processing with cuCIM.
We're going to look now at an example of interactive image processing where we're going to explore the parameter space in real time. And in this case, we're going to use Napari with a package called Magic GUI developed by Tali Lambert, which makes it easy to make a fairly simple plugins to Napari, where you'll have sliders for different inputs to the function and so forth, which gets set up for you by adding this kind of Magic GUI decorator to an existing function. And so in this case, what we're going to start with is an image of the retina, which corresponds to one of the sample images from this Kaggle competition on diabetic retinopathy detection. And what we're going to do here is start with the apply ridge filter function, where we have basically a combo box that's going to let us choose between different filters and then some other sliders and things that let us vary parameters of those filters. And what goes on in this function is basically you're going to read in this retina image called cuPy.asArray to transfer it to the GPU, RGB to gray to convert to grayscale, and then we're going to retrieve the requested function from the filtering module, apply it with these provided parameters from the GUI, and then on the output of that, we're just going to rescale it to a 0-1 range. And then we hook this plugin into Napari and call run here. So if we run this from the command line, we should get a Napari window popping up that has these controls over here at the right that correspond to the widgets created with that magic GUI wrapper there. So this is our retina image, and if I select one of these, it's going to apply the filtering, but as you notice, I've already selected it. It's still computing here because this image is somewhat large, a few thousand pixels per side. So it takes a little bit of time for this to compute and update. And so we see it there, and I can kind of scroll back and forth to see this, whether these vessels look like they're lining up well with the original image, which it does. But that took several seconds for that result to show up, so it's not really practical to play around a lot with changing these sliders and going through the different filters. If I switch this now to selecting use the GPU, now I can switch back and forth between different filters, and it will update relatively quickly. So let's go back to Frangie here. So that's updated. If I change the range of these sigmas, I'll see that fairly quickly in the main window here. And it's easier to explore this place and figure out appropriate parameters I want to apply. And obviously this can apply to many other things. In these particular filters, you may have something like image restoration or image registration where you want to vary parameters and verify some result in the window. And this makes that more feasible to do in an interactive manner.
For this last demo, we're going to look at image processing with Dask. Next slide. And in this usage of Dask, there's a couple of common scenarios. The general concept is that we have some large set of data that we want to break up into smaller chunks, and we want to process those chunks separately. This could be either we want to process in smaller chunks so we don't need as much peak memory on the GPU, or it can be a case where we want to process more chunks in parallel so we can make better use of things like multi-threading or even distributing the chunks across multiple GPUs or multiple workstations. So
this demo, we're going to be looking at some volumetric data. So I'm scrolling through here along a sagittal plane of ex vivo MRI scan of the brain. And here the front of the brain's here on the right side. And this is actually a series of 4 acquisitions with subtly different contrast. And so this data itself is too big to fit on the GPU at one time, or at least to process on the GPU all at one time. And so we're going to look at how we can break up that processing into chunks using Dask. So what we want to do here is we're going to use a function from the restoration module of cuCIM's scikit-image. The data itself corresponds to this publication of Edlow et al., where they collected MRI data at 100 microns ex vivo. We've downsampled that to 200 microns here so that it runs quickly for our real-time demo here. And if I run this script, it's going to first print out some attributes of the shape. We see there was 4 acquisitions and there's several hundred elements along each spatial axis. We've divided this up into a total of 100 chunks with 4 to 5 along each spatial axis. And so we're going to set this to use the GPU, in which case it's going to run this function, which copies data. It takes one block as input. It's going to copy that to the GPU, take the mean along these 4 acquisitions, and then apply this total variation denoising to the spatial axes before copying it back to the host. And so the way we apply that over all blocks is using Dask array's map overlap function, which takes a function that you want to apply to each block in this array. We've specified here that we want to pad each block a little bit to avoid boundary artifacts between the blocks. And this drop axis is indicating that the output is going to have, it's not going to have axis 0 anymore of what was in the input, because we have taken the average along that axis, so it's no longer there. And finally, we can use Dask array. Dask has this toZar method on the output here that we can call to write this out to another ZAR file on disk. It's going to write out these chunks as it computes things. And so this has finished here. It took about 12 seconds running this on the GPU. And if we go to inspect what that looks like, we're zoomed in a bit here. You can see the graininess in the, this is actually the average across the 4 acquisitions now. But if I make that layer transparent, we see the denoised result underneath. And can see that a lot of that graininess is gone, but we've still kind of preserved a number of these details, such as the kind of hyper intensities here in the gray matter and the cerebellum and so forth. So this is a way to process larger data in a blockwise fashion on the GPU.
For those interested in more, so we saw using Dask on a single workstation there, but for distributing across multiple GPUs, there's a good example of that for deconvolution. It's not using cuCIM, but the same technique can be applied to functions from cuCIM, and this is shown in NVIDIA's, or in Dask's blog at the link shown down here. So at this point, I'll go over a few of the future plans and how you can get involved. We're looking to continue to improve the scikit-image API coverage. We currently have around 2/3 of the functions covered. And we would like to also, on the I/O side, support a number of additional image formats, from kind of basic image formats to things that are common in fields such as digital pathology, the DICOM format from radiology, as well as other things like OME ZARs and the next generation file format. We're also interested in expanding our demos, and particularly in those on the next slide, demos that illustrate interoperability with other libraries and frameworks. So there is a lot of potential via these protocols to interact with these libraries. So we'd welcome any of you watching to contribute. Bugs and feature requests can be raised on our issues page, and we welcome code contributions from the community. We currently recommend installing cuCIM via the Conda package manager as shown here. And although finally, just want to highlight that we have various examples available in our repository. There are some small ones available there, as well as a repository created with scripts corresponding to the demos shown in this talk. We would welcome your feedback, including not just bug reports, but how you're using the library or features that you would like to see in your field of application. Thank you very much.
Thanks, Greg and Gigan. So we have a few questions here in the Q&A. The first one is, are you expecting that cuCIM will be integrated with Dask?
So cuCIM itself doesn't know about Dask, but Dask supports the cuPy arrays in addition to NumPy arrays, and that's what's the basis of all the cuCIM.scimage functions. And so it should be possible to use cuCIM functions in combination with Dask, as we showed a little bit in the demo there. And we'd like to, I should also point out there's a Dask image package, which works with cuPy arrays following some of the SciPy and image API.
Thanks, Greg. Another question, what kind of GPU do you have on the computer running the demo?
These were the ones that we showed here. We're using a GTX 1080 Ti. Some of the bar charts earlier on had an additional A100 model as well, with the interactive or the videos at the end or the 1080 Ti.
Thanks, Greg. Another question, for file I/O, we usually think of disk bandwidth as the performance bottleneck. What were the performance bottlenecks that were addressed for the OpenSlide accelerations and compressions?
Yeah, to accelerate OpenSlide library, we try to optimize the two parts. First one is decoding library. cuCIM uses faster libraries such as libjpeg turbo and libdeflate, and we have a plan to support GPU accelerated libraries, including GDS, MVJPEG, and MVJPEG 2000 to load and decode JPEG images directly on GPU. The second one is the use of cache to avoid redundant image load reads. OpenSlide uses a fixed amount of cache memory per file handle, and the cache is not configurable. So cuCIM implemented programmatically configurable cache mechanism and used the high-performance concurrent hash table library.
Thanks, Gigan. Yeah, so that looks like all the questions that we have here. So thank you again for your presentation. And hopefully others can find you at SciPy if they have more questions. Thanks again.
Sure. Thanks, John.
Thank you.